Welcome to our video tutorial of dimensional modeling and data warehouse design. My name is Chi Su, and I'm here with my teammate Anisha Matthews. This video is a project for CIS 540 Data Warehousing and Mining with Professor Chen Wang and for the School of Cal State Dominguez Hills MBA program. Hi everyone. Today, we are going to go over the basic principle of dimensional modeling. Dimensional modeling is a bottom-up approach of warehouse design developed by Ralph Kimball. The process of dimensional design is done in 4 steps, which include Step 1, select the business process. Step 2, declare the grant. Step 3, identify the dimensions. Step 4, identify the facts. We will discuss each step with more details in the later slides. The first step of dimensional modeling is to select the business process. A business process is a collection of related structural activities or tasks by people or equipment which in a specific sequence produce a service or product for a particular customer or customers. For example, taking orders, checkout at the grocery stores, taking customer application for credit cards, shipping orders for customer, and etc. It's important to choose a process that's both critical and feasible. You need to consider the type of a business or organization you're working for, what's the objective or the mission of the business, and if the data is really available. In our tutorial, we'll be using retail store as an example to design a data warehouse. A good example of critical business process in a retail store is point of sale system. If we simply look at the receipt of the sale, we can find things like product sold, the store number, the sales clerk, the day and time of the sales, is there any discount, and the total dollar amount of the sales. All of these data can be used to build a data mart and perform data analysis and business intelligence. As step 2 of dimensional modeling is to identify the grant. During this process, we identify the granularity of a fact table. We'll go over fact table in step 4, but for now, let's focus on the grant. You can think of grant as a single row in a fact table. Depends on the level of detail you want to be made available to the dimensional model. The more detail you need, the lower the level of granularity. The granularity of a dimensional model that consists of date, store, and product can be used to study a product sold in the store by a specific date. So for example, we can use the data from the points of sale system to find out how many Sony TV were sold during Black Friday, November 29, 2019, in the Carson store in the city of Carson. After we declare the grant, we can then move on to identify the dimensions that match the granularity of our model. So continue with our example from last slide. We want to know the product sold in store by date. We can lay out this data into 3 dimensions. The product dimension that contains the product key, product name, and product category. The store dimension that contains store key, store number, and street address, city and region. The date dimension which contains date key, the date, month, quarter, and the year. Each record in dimension table should have a primary key. These keys are used to identify the dimension table and will be used as a foreign key in the fact table. They are being used as a reference to dimension table and joined in fact table. The final step of dimensional model design is to identify the fact. Fact table, like dimensional table, must be true to the grant declared in step 2 as well. Fact table help answering the question, what is the process trying to measure, what needs to be analyzed, or what we are trying to get out of the data warehouse. In the retail sales, we may want to know how many toilet paper people buy at once in a particular store on a particular day. So we'll need the sales fact table with all the number representing each order or transaction, what product was sold, how many of such product was sold, and on what date.
In this section, we will cover the dimension table details, which include the date dimension, the product dimension, the store dimension, the promotion dimension, and the retail scheme in action. The date dimension usually is the first dimension for the underlying partitioning scheme of the database. This way, the successive time interval data loads are placed into the territory on the disk. This is one dimension that can be built first for your retail sales data warehouse, unlike the other dimensions that will be included. At one point, this dimension table was referred to as the time dimension table, but has changed to be named the date dimension. This has been changed to mean a daily grain dimension table, and it helps tell it apart from the time of day dimension. If you look at the example to the right, this is a partial list of columns for a daily date dimension table in the retail environment. When looking at the columns, for example, the day of the week column would contain the day's name. Examples are Wednesday, Friday, or Saturday. This can be used to create reports to compare the sales for the business on the different days of the week. For reporting purposes, the year-month column is useful for a column header, and using a quarter number would be useful. This example shows the sample rows containing several date dimension columns. As you can see, we have our date key, date, full date description, day of the week, as mentioned earlier, our calendar month, quarter, year, fiscal year by month, if we have any holidays, and the weekday indicator. Looking over the second example on the right, this is a sample report showing cryptic versus textile indicators. When looking at the holiday indicator on both reports, you see the yes-no output versus the holiday non-holiday output. Both reports are the same, but we see more meaningful domain values for the second report, and the information is more self-explanatory. Same would hold true for a weekday indicator. We would not want to use a yes-no, but weekday or weekend indicator. Multiple date table attributes can be jointly constrained, so you can easily compare weekday holidays with weekend holidays. There are attributes that can be added to basic data dimensions that will change over time, including its current date, its current month, its prior 60 days, and etc. Its current day will be updated daily, can generate reports that run for today. Most data warehouses load data daily. The is current day will refer to the most recent day loaded. Adding attributes that are unique to your corporate calendar can be done. Such an example would be is fiscal month end. This attribute could easily be a computed column rather than physically stored. If you change the grain of this dimension to 1 row per minute in a day, there would be over 10 million rows to accommodate the 1,440 minutes per day. And if time was tracked to the second, there would be more than 31 million rows per year. Therefore, the date and time dimensions are kept separate. Product dimension. The product dimension describes every SKU in the store, when accounting for different merchandising schemes and historical products that are no longer available. The product dimension may have 300,000 or more rows. The product dimension is almost always sourced from the operational product master file. Most retailers administer their product master file at headquarters and download a subset to each store's POS system at frequent intervals. Headquarters' responsibility is to define the appropriate product master record. The merchandise hierarchy is an important group of attributes. To the right is a product dimension sample rows. Included in this product dimension is the product key, product description, brand description, subcategory description, category description, department description, and fact content. There are 300,000 different values in the SKU description column. There are 6,000 repetitions of each unique value in a department attribute. Dimension table space requirements pale in comparison with fact table space considerations. It often makes sense to combine a constraint on this attribute with a constraint on a merchandise hierarchy attribute. Often, operational product codes have embedded meaning with different parts of the code representing significant characteristics of the product. Multi-part attributes, in this case, should be both preserved in its entirety within the dimension table and broken down into components parts. An example of this is the 5th through 9th characters in the operational code identify the manufacturer. Then the manufacturer's name should also be included as the dimension table attribute. Sometimes you will encounter numeric values that will not fall into either fact or dimension attribute categories. The list of a product would fall into this example. The standard list price will change infrequently, unlike most facts that often differently values on every measurement event. If the value is used for calculation, then it would belong on the fact table. If it is used primarily for price variance analysis, then the variance matrix should be stored in the fact table. And if the stable numeric value is used for filtering and grouping, then it should be treated as a product dimension attribute. Sometimes it can serve both calculation and filtering grouping functions. When this comes about, it should be stored on both the fact and dimension table. Store dimensions. The store dimension describes every store in the chain. Unlike the product master file that is almost guaranteed to be available in every large retail business, there may not be a comparative store master file. Project teams assemble the necessary components of the store dimension from multiple operational sources. Each store in the store dimension can be thought of as a location. Stores can be rolled up to any geographic attribute, such as zip code, county, and state in the U.S. Cities and states in the U.S. are not a hierarchy. Since many of the states have similar named cities, include a city-state attribute in the store dimension. Store would also roll up into organization hierarchies, which would include districts and regions. To the right is a retail store dimension table. The floor plan type, photo processing type, and finance service type are all short text descriptors that describe the particular store. The character codes for these should be 10 to 20 character descriptors that make sense when viewed in a pull-down filter list. The first open date and last remodel date in the store dimension could be date type columns. Date dimension copies are declared in SQL by the view construct and systematically distinct from the primary date dimension. Now the system acts as if there is another physical copy of the date dimension table called first open date. The promotion dimension describes the promotion conditions under which a product is sold. Promotion conditions include temporary price reductions, in-aisle display, newspaper ads, and coupons. It is called a casual dimension because it describes factors that to cause a change in the product sales. Promotions are generally judged on one or more factors. Whether the products under promotion experienced a gain in sales, called lift, during the promotional period. Lift can be measured only in the store can agree on what the baseline sales of the promoted product would have been without the promotion. Whether the product under promotion showed a drop in sales just prior to or after promotion, canceling the gain in sales during the promotion, time shifting. Whether the product under promotion showed a gain in sales, but other products nearby on the shelf showed a corresponding sales decrease. Whether the products in the promoted category or products experienced a net overall gain in sales considering the time periods before, during, and after the promotion, and whether the promotion was profitable. Usually the profit of a promotion is taken into an incremental gain in profit of the promoted category over the baseline sales, considering time shifting and cannibalization. An example of a promotion dimension table is on the right. The promotion dimension must include a row with unique keys such as 0 or -1 to identify the non-promotion condition and avoid a null promotion key in the fact table. Referential integrity is validated if you put a null in a fact table column declared as a foreign key to a dimension table. Null keys are the source of great confusion to users because they can't join on null keys. Sometimes nulls are encountered as dimension attribute values. These usually result when a given dimension row has not been fully populated, or when there are attributes that are not applicable to all the dimension rows. Substituting a descriptive string such as unknown or not applicable in place of the null value. Also, nulls can be encountered as matrix in the fact table. Leave these nulls so that they're properly handled in aggregated functions such as sum, min, max, count, and average, which do the right thing with the nulls. Substituting a zero instead will properly skew these aggregated calculations. Retail scheme in action. Here's an example of a retail sales scheme. With the retail POS scheme designed, this is how it would be put to use in a query environment. If a business user is interested in a better understanding of weekly sales dollars volume by promotion for the snacks category during January 2013 for a store in the Boston district, query constraints on month and year in the date dimension, district in the store dimension, and category in the product dimension. This example shows the query results in cross-tubular report. When we look at the dimensional model and the query results, we can see the relationship. High-quality dimension attributes are crucial because they are the source of query constraints and report labels.